Hello, welcome to the day 4 of second week of this lecture series. I hope all of you are doing well. We have been trying to figure out whether we can find out the point groups of different molecular structures. In the last class we looked at the structures of hydrogen peroxides, and we saw that for hydrogen peroxide I can have two different structures. One is the planar cis when we considered the planar configuration. So we got C2V point group for cis planar, while we got C2H point group for transplanar. Right. So I guess you still remember what were the symmetry operations. In case you have not, then let's again look at those. So for C2V that we got for cis planar configuration of H2O2, we got the following symmetry operations. So we had E, we got C2, we got two sigma V's which are differentiated as sigma V prime. While so this is a group, and for transplanar configuration we got identity, we got C2, we got sigma H, and we got the inversion symmetry. Now if I ask you, can you tell me what are the orders of these groups? Both of them have 4 elements. Okay, in a group there are 4 elements, and each element is a symmetry operation. So the answer is 4 for both of them. Okay, so order, we have mentioned it earlier, of a group is equals to the number of elements in it. Okay. So in case of symmetry point groups also, all the symmetry operations, when you have found all the symmetry operations belonging to that particular group, so you form a closed group, and the number of such symmetry operations including identity will give you the order of the group. And in many cases you will be using a notation called H. H stands for order of the group. In some books you will find out that symbol for order, but it does not matter. We mostly will use this term H to define the order of the group. Now one more thing, have you noticed about this particular groups? Some kind of relations that you can figure out which exists among the symmetry operations. So you should think a little bit about it. Okay, later on maybe we will come back to this topic again. So what we will do today, we will continue looking at some more molecules, molecular structures, and we will find out their point group symmetries, okay, systematically. You remember we had shown a nice flow chart which is a systematic procedure, which describes a systematic procedure to find out the point group of any given molecular structure when you know all the symmetry operations for that particular molecular structure. So we will use the same scheme and try to find out point groups of certain molecules. So we will go from simpler to little harder problems. So the next molecule that we will look at is on your screen. So this is 1,3,5,7 tetramethyl cyclooctatetraene. Okay, the structure is given here. So for this molecule, you what are the symmetry elements you can find out? Okay, the symmetry elements, or if you say here directly symmetry operations, identity is by default it's present there. What are the other elements that you can think of? Does it have any proper axis of symmetry, proper axis of rotation? You don't really see a proper axis of, axis of rotation which is not a consequence of something else. By something else, what I mean is an improper axis of symmetry, which is indicated here. So, rotation about this axis by 90 degree followed by a reflection perpendicular to this axis will give you an indistinguishable structure. You can just verify that one. So, if I put a star on this particular methyl group, then a 90 degree will take it to somewhere here, right. So, from here to somewhere there, and then when you invert it, so the carbon which was protruding outside, it will be going in below the plane of the paper. So, that will actually come here, while the guy sitting here will now move up here. So, ultimately you will get back an indistinguishable structure. So, there is a valid S4. Now, if there is an S4, we have learned in the one of the previous classes that for an even order improper axis of symmetry, when n is greater than 2, okay, in that case one always will have a proper axis of symmetry which is like Cn by 2. Okay. So, here we have S4. So, S4 will automatically give you C2. So, C2 must be present. So, if you again think about this particular axis, this S4, if you imagine C2 axis there, you will see that really there exists and C2 about the same axis. So, you can figure it out like this portion which I have made this given this star symbol. So, this will come over to this place and this guy will go here. So, ultimately you are getting the indistinguishable structure. So, there exists an C2, but this C2 is not a natural not a proper axis of symmetry or principal axis of symmetry by its own merit, but this is a consequence of having an even order improper axis of symmetry. So, by rule, we had this step 1, 2 and 3. So, if you remember that step 3 that we looked at, so found that okay, is it like S4 is the only Sn axis of even order is the only symmetry that is possible? Yes. So, I can generate C2 from S4 itself. So, this point group you can easily now figure out for this particular molecule. So, let us move on to another molecule which is cyclooctatetraene. Now, you see in the previous example as well as this current example, it is very vital to know the structure, and that is why I in the one of these previous classes I mentioned that in order to find out the point group, first thing you have to do, you have to find out the structure of the molecule or the shape of the molecule. For that you can use this the Lewis structure and apply VSEP theory and find out the structure and the shape. Then only you can actually visualize the symmetry operations that may exist in those molecular structures. So, here like when I look at the cyclooctatetraene, you need to know that this is a 3-dimensional structure like what is shown on your screen. So, it's like a boat, right. So, the cyclooctatetraene also it has an alternating double bond. Now, if you look at this structure, what you have here, just like the in a previous case, you have an S4, but here other than S4 there are other symmetry elements. So, you can see that we have pointed out here, here is one axis which joins this point and this point. This is a C2 axis. So, if you rotate 120 degree, you will get back the indistinguishable structure, and so is this axis. So you have two C2s, and this C2 is perpendicular to this axis, which is S4, and obviously it will have a C2 axis as well coinciding, okay, on the same axis. So you essentially have now C2 and two perpendicular C2 primes. So this molecule definitely belongs to D type of point group, right? So without worrying about anything, I can write it's D, and here the principle of axis of symmetry I have, because it's not the S which is only present here. So other than S also are there. So I have a C2 and two perpendicular C2s to this original C2 axis. So it belongs to D, and since the principal axis has an order 2, because C2 means the order of rotation is 2, so immediately you can write up to D2. Now then you have to ask the next question, that whether there is a sigma H. Okay. So now looking at this molecule, do I see any plane which is perpendicular to this C2 or S4 axis that can give you an indistinguishable structure? And the answer is an obvious no, right? So I cannot really have this reflection symmetry which is based on the plane perpendicular to C2 axis. So there is no sigma H, but there are sigma D's. Okay. So the moment I know that there are sigma D's, I have to find out how many sigma D's. So it demands that I should have at least 2 sigma D's. Then I can call this point group as D2D. So let's find out. So I have this 2 C2 primes, right, here and here, and the definition of sigma D's, that is for a sigma plane to be called sigma D, that plane has to bisect the dihedral angle formed by the principal axis and the two perpendicular C2s. Okay, or you can say that okay, it can also bisect this C2 prime, the angle created by two C2 prime axis. So I can have an plane. So if I can draw the plane symbol like this, so one plane will be here and another plane will be on this plane. Okay, so if I can draw the plane like this, so I have 2 sigma D's. So I write sigma D and sigma D prime. Okay, so I have 2 sigma D's. So now my point group is complete. So this molecule belongs to point D2D. So you have everything explicitly written here also, so you can go through this one so that you can understand it better. So let's move on to some other molecules. Benzene, we have been showing you the benzene models, okay, and this is probably one of the simplest thing that you know. So the benzene we have already seen that it has a principal axis of symmetry which is perpendicular to the plane of the screen. Okay, so there are hydrogen atoms. I am not drawing the pi cloud here. So assume that pi cloud is there and that is symmetric, so it should be implied. So now you have along if I can imagine an axis which is passing through this point and perpendicular to this plane of the molecule, then that is my C6 axis, right? And I do not have any other C6 axis. Fine. So C6 is my principal axis of symmetry. So proper rotation is there, and obviously this for this molecule I don't have to care about possibility of any special groups, because it's not that only sigma is there or only I is there. It's not linear molecule, and since I can see that C6 is there, It can generate a lot of other symmetry elements. I can see a lot of planes there, lot of perpendicular C2s there. So they have many other symmetry operations. So we directly go to step 4 and 5. So in order to go to step 4 and 5, what we have to do, we have to ask a question. Okay, are there 6 C2s perpendicular to this C6? So the question we ask is 6 C2 primes. Let's see. So I can imagine an axis here. So this is very obvious to us, right? So if I give an 180 degree, I get equivalent structure. So this is one C2 prime because this is perpendicular to my C6. Similarly, I can add these two opposite hydrogen atoms. So already I got 3 C2 primes. Now similar to these C2s, there are other C2s, right? So like this, and like this. So I got my 6 C2s. So the answer is yes. So automatically my point group will be D6. I have not completed yet, but it will be D6 followed by something. Okay, either H or D or nothing. Let's figure that out. So now the following question will be, is there a sigma H? And answer is pretty obvious because this molecule is planar. So and your principal axis of symmetry is perpendicular to that molecular plane. So the molecular plane for a planar molecule always hosts a plane of symmetry. So this plane of symmetry is perpendicular to the principal axis of symmetry C6. Hence, I have a sigma H. So if the question is asked sigma H, so the answer is again yes. So ultimately my point group is D6H. So that is very easy. Now you can see that there are a lot of symmetry elements present there, and then there will be a lot of symmetry operations generated from that. We can now find out what is the point group for a given molecular structure. And in many cases, we don't have to even go and find out all the symmetry operations, because now we have learned a little bit that okay, what are the main things that we should look at in order to find out what is the point group. So that's why I didn't look at any other possibilities, but you can have a quick look at this structure again for benzene, and you can see there is an inversion center, right? You start from any hydrogen, pass through the origin, the center point of the benzene molecule, go to the other direction, the same distance, you will find identical hydrogen there. So there is an I. So there will be improper axis of symmetries. There will be many other sigma planes which are not in the molecular plane but perpendicular to the molecular plane. So there will be 6 sigma planes there. Okay. So there are so many other symmetry operations. Now there will be a question that if someone tells me a point group, can I find out what are the symmetry operations that this particular group can have? The answer is yes, obviously yes. So there are techniques by which you can find out. So which I will talk about in the following week. Okay. So you remember that we will be discussing about the possibility of finding out the symmetry operations from the point group symbol. So one thing I forgot to tell you, I should have these notations that we are using to symbolize a particular point group like C2V, C2H, D2, D2H, D2D, whatever. These notations are called Swain-Flies notations. Okay, so that's for your information. So now let's move on to some other molecules again. PF5, that must be by now very easy for you, right? PF5, what will be the structure? The first structure we can think of is a trigonal bipyramid. Okay, so let me erase the rest of the part. So PF5 will have a structure something like this. oops, okay, so every corner there will be one fluorine, and in axial direction there will be one fluorine, while here there will be one more fluorine, and phosphorus will be sitting here. So now what are the symmetry operations? First, like we will look at the principal axis of symmetry. What is the principal axis of symmetry? You can see for every 120 degree rotation I can get an equivalent structure. So there is a C3. Fine. Now next question to be asked is there any perpendicular C2? So what will be the answer? Answer is easy, right? So I can see one C2 here, because this 3 F's in the equatorial plane will form as if an equilateral triangle. So you start from one tip of the equilateral triangle and go till the mid of the base, you get an axis which is nothing but a C2, right? So this is one C2 prime because it is perpendicular to the principal axis of symmetry. So principal axis of symmetry is along this, as we wrote already, C3. So since I have started with one tip of the equilateral triangle and got extended to the base and got my C2 prime, so I can similarly find other two C2 primes if I start from other two tips and reach to the respective bases, right? So similarly I get one C2 here, another C2 here. So I got 3 perpendicular C2s, that is 3 C2 primes. So my point group belongs to D type, that much we know, and it will be also D3 type. Now is there a sigma H? Yes, this molecule, this equatorial plane act as a mirror plane, right? So the top fluorine will be reflected here and this will go here. So I have a mirror plane which is in the molecular plane and perpendicular to the principal axis of symmetry. So I have the point group right now, which is D3H. So that was easy, right? Okay. Now you will see how important is to know the structure in this and even in some of the following examples. Okay. So we are going to talk about ferrocene. Ferrocene is, you have an iron and then 2 cyclopentyl groups. So how it look like? So it depends, right? So 2 cyclopentane rings will sandwich the iron at the center. Now these 2 cyclopentane, they can be, they freely can, they can rotate freely. Okay. So they can have an eclipsed conformation and they can have a staggered conformation. So if I take this ferrocene molecule and look from the top, okay, and if the molecule is in eclipse conformation, what do I have? I have something like this, right? Because I am looking for the top. In reality, it will have a structure which is like almost like a a dumbbell kind of shape, right? A sandwich structure. On the other hand, the eclipsed, on the other hand, the staggered conformation will have something like this. So okay, fine. So now we have to find out the point group for eclipse and staggered, okay, conformations. Let's start with the eclipse, which is the easiest. I tell you at the very beginning, this will have a D5H point group. Why? It's a pentagon, the cyclopentyl group, and all the CC bond distance are same, right? So for every it will be what will be the angle? It should be 360 degrees by 5. So it should be 72 degrees. So every 72 degree rotation, will give me an indistinguishable position about this axis. Okay. So, this is my ferrocene molecule. So, axis passing through the center of one cyclopentyl group iron and then the center of another cyclopentyl group, that will be my C5. So, these two are eclipsed. So, a plane which is perpendicular to this C5 and containing the iron will reflect the top part, that is top cyclopentyl group, to the bottom and vice versa. So, I have a sigma H, right, and this is as cyclopentyl group. So, just like the PF3, I can have C2s which are perpendicular, right. So, I can find out all the possible C2s. So, there will be total 5 C2s which are perpendicular. Okay. So, I have C5 as the principal axis of symmetry, I have 5 C2 primes and I have sigma H. So, this becomes T5H point group for eclipse conformation. Now, what about the staggered conformation? Okay. Here, what do I have? Do I still have C5? The answer is yes, I have C5. So, you can figure this one out, because this one will move here, similarly this one will move here, right. So, I will not find any distinguishable change there. So, C5 still exists in this staggered conformation. Now, what about perpendicular C2s? So, now let me use another color so that I can separate this. So, let me use something like green. So, now say this is my top cyclopentyl group and the other one that is in red color, that is at the bottom. So, I am discussing the possibility of having a C2 prime here. Now, we had C2 prime for this eclipse conformation, right. So, along this there was a C2, correct. Now, do I have a same kind of possibility here? Suppose I have I draw axis through this. Now, what will happen after performing a C2 type of rotation, okay, along an axis which is similar to this, okay, here also? This top green part will now go to the bottom, okay, and this red part which was at the bottom will come up here. So, this green part, it will go to the bottom, not only go to the bottom. So, like this tip of my this finger is this point I am talking about. So, this will now flip completely, and this part which was projecting toward you will now come in this side, that is projecting toward me, okay, and is in the bottom hemisphere, just like this. Similarly, the red part which was like flat, the red part which was like a tip here, so that will go above here. So, ultimately I have a C2 which is perpendicular. So, very easily I can find out other 4 C2 primes. So, I have essentially 5 C2 primes. Now, the question is sigma H. Here I do not see a plane which will give me an indistinguishable structure upon reflection on that plane, and particularly the plane which is perpendicular to the C5 axis here. So, I do not have any sigma H. Do I have a sigma D? Yes, I do. So, any of this sigma D's will be very easily found, because I have the C2s now. So, for taking, if I find out any two adjacent C2s, if you have a plane which contains the principal axis of symmetry and bisects that angle formed by two C2 primes, you have got your sigma d, and you should be able to do that, okay, using pen and paper very easily. So you will see, if you perform that, you will see there are 5 sigma d's. So that is sufficient to get the point group. So I have d 5 t point group for the staggered conformation of ferrocene molecule. Okay, so we will stop here today, and in the following class I'll look at a few more quite complicated molecules, and then we will also learn about some properties of the symmetry operations, and we also will try to find out if the certain physical properties like polarity or chirality and hence optical isomerism with the symmetries of the molecules, and therefore with the point group of the molecule. So see you tomorrow again. Thank you very much.